this year. And David, I don't know, because many people, you may be knowing David. He's Susan Eckert Lynch Professor of Science and Business at Charles H. Dyson School of Applied Economics and Management at Cornell University. Of course, he has his doctoral degree from Cornell University and master's from Berkeley. And his research interests, of course, are varied. These include economic impacts of agriculture and food policy, risk and production, consumer and producer acceptance and use of biotechnology, food assistance and nutrition, and consumer behavior. Dr. Just is a very prolific writer and publishing in very high impact journals. He is on the editorial board of several journals, including American Journal of Agricultural Economics, Food Policy, and so on. There is a huge list of his excellence, I would say, in agricultural economics research. So today, we had requested that Dr. David was here about a month back. So we were just discussing what can we do in collaboration together. Then we decided, okay, let's listen first to David in our lecture series. And then, of course, his ideas for collaboration with us. Today, Professor David, he will be delivering a lecture on risk choice, lottery selection, and probability weighting, testing robustness of extremes. And probably, I think the extreme, what you mean is maybe the climate extremes, which are becoming very important. So I don't know what do you mean by extreme, but with these words, I again welcome you and invite you to deliver the lecture.
Yeah, that's it.
And all of my colleagues, we are sitting here in our common committee room.
Very good. So yes, that question of extremes and what I mean by it, I'll cut to the chase and say what I'm looking at in terms of extremes are extreme amounts. So large risk in terms of dollar amounts, and extremes in terms of probabilities. So probabilities that are either extremely small or extremely large. Okay, I'll acknowledge this is some work that I had been doing with a PhD student that was here. The PhD student is now graduated and is in a tenured position in Thailand. So I want to acknowledge her work on this and leadership as well. And it's going to take me a little bit of time to sort of work into this, and I hope you'll follow sort of the setup. The theory behind this is really important. So when it comes to decision under risk, there are a whole bunch of different models that have been proposed, but expected utility theory is sort of the king of those models, right? It's the model that basically everybody starts out with and everybody uses if they're doing applied work. And there are a couple of modifications to it that some people employ. But by and large, most things are still done in utility theory. We know that expected utility theory has problems. We know that there are ways in which it doesn't predict behavior and ways in which it is violated by the behavior we observe. But it has these really sort of attractive, rational foundation to it, which is why I believe economists continue to use it. One of the key ways in which it's been modified to try and account for some of those violations, if you will, is called probability weighting. And almost all the alternatives to expected utility theory use what we call probability weighting in some way. And I'm going to talk a little bit about what these probability weights are and where they come from and how we know what they look like. The sort of key stylized facts behind them are that people tend to overweight small probabilities and underweight large probabilities. And those key facts have driven a lot of applied work looking at insurance and people's willingness to insure against extreme events and things like that. So it has pretty big relevance for a lot of the work that applied economists do. And what I want to ask here, and what we're really trying to get at, is this really robust? Are these models that have been proposed, alternatives to EU expected utility, are they robust to very small probabilities and large rewards? And that's going to be an interesting answer. I guarantee you. I'll try and get to that as quickly as I can. Okay, so risk literature, and I will say, stop me if I am incomprehensible, if you need clarity on something I'm saying. There are a series of findings that present a challenge to our understanding of risk behavior. Some of these have to do with the model, right? We have a whole bunch of experimental literature that shows that our models don't really predict what people are choosing in an experimental lab setting. Some of that has been extended out into the field, and it suggests maybe we really don't understand what drives people's decision in this context. There are some findings out there that are empirical strategy, particularly in agricultural applications, to estimating people's risk preferences and their risks. They get confounded in such a way that it is hard to disentangle, what is risk perception versus risk preference, and what is actually the risk that they're perceiving, right? One of the big sort of problems that we run into with this, which I'll hold off a little bit in going too far into it, is we can't see what the risks are as researchers. We can observe the outcomes, but we can't observe what people are perceiving in terms of the risks that they face. And so that causes a real big empirical problem in trying to estimate what the decision drivers are. Even the concept of risk preferences, though, has sort of begun to be debated, and whether people are actually perceiving risk and what risk is the same way that economists define it. And so the big question is, have we really sort of taken our models and our theory so far out that our empirics can never have a hope of actually catching up and being able to identify these things? And we're going to use some novel decisions to try and get at this question in a way that I have not seen done in the literature before, and in a way that actually reveals something pretty important in the end. We end up finding a new puzzle, if you will, that is pretty hard to reconcile with probability weighting. And so this casts some doubt on whether probability weighting is really the right way to go, in my mind. And so, like I said, what's special about risk? The fundamental problem is that we cannot necessarily agree with the people we're studying about what the risk is, right? When we study the sale of rice, it's pretty a good bet that the person selling it, the person buying it, and us studying it, we all have an understanding of what rice is. But when we talk about risk and people buying and selling insurance or making decisions about how much to plant and this, that, or the other, and they're facing risk, we can't observe it, and we don't know what's in people's heads. And so we have to estimate what it is that's being chosen between, not only the thing that is chosen, but the opportunities that were passed up as well, which are never observed. And this creates a really severe empirical problem that is thorny, right? And that's driven a lot of some of the recent literature in risk. And so some of that literature is going to be important here. I'm going to use some of that and give you some definitions to sort of help hang your hat on what it is that I'm talking about. Some of this, the puzzles that started popping up weren't just in the lab, right? We did have some of these that popped up from estimates in various fields of economics. We've got a theory of expected utility theory that tells us something about how people should behave and what ranges we should see for measures like relative risk aversion and absolute risk aversion. In particular, if you follow Arrow's arguments, relative risk aversion should be somewhere close to 1, and by close to 1, I don't mean like within epsilon of 1, but in probably between something like 1 and 3 has been what people suggest in the theoretical literature. But when we estimate using empirical data from stock trades, we get something around 330, 300, sometimes 3,000. We get numbers that are just outrageous and seem like they're beyond what our theory could even possibly explain in terms of how risk averse people are. And when we look at farmers in particular, we get these numbers that are also very large. People have tried to estimate and test for decreasing absolute risk aversion and increasing absolute risk aversion. Our theory says DARA is what we should observe, but we actually have a hard time discerning it, right? We find IARA about as often as we find DARA. And if it's really that, I don't know, wobbly, are our empirics really telling us something, or are they just, is it noise, right? That's part of the question behind this. In terms of lab experiments, Allais was the first one to sort of demonstrate the failure of EU in a lab setting, use hypothetical choice to do it. But we've substantiated all of his results using motivated choices. And it's been replicated hundreds of times, thousands of times. We do this every year in my behavioral economics classes, and our students don't behave according to EU. All of the axioms, the rational axioms that underlie expected utility theory, are violated with regularity under the right circumstances. And so the question is, well, are these experiments representative of the types of behavior we see in real life? Or are we putting them in circumstances where the model breaks, but aren't particularly relevant for the real world? And that's actually a really interesting and useful question, one that we don't quite answer here, but we come close. How do we find those violations of expected utility theory? It's helpful to think about this. This is called the Marshak-Machina triangle. And when you have the Marshak-Machina triangle, it represents a set of gambles that all have 3 outcomes. And here I'm going to say there are 3 outcomes. One is $100, one is $0, and one is 50, right? So you always organize this so the probability of the largest outcome, dollar outcome, is on the vertical axis, probability of the lowest is on the horizontal axis, and the remaining probability from any point is assigned to the middle outcome. Okay, so you have this triangle that represents all possible gambles with those 3 outcomes. And expected utility theory, just by using the simple formula for an indifference curve, right, that the sum of the probabilities times the utilities is equal to some constant, you find that the slope of your indifference curve has to be a straight line, and it also has to be parallel. In other words, all indifference curves have the same slope. And that tells us that if we were to take any pair of gambles on a particular line in one part of the triangle, and we ask people to choose between those 2, if we had a line that was right here, right, and somebody chose the gamble that was located right here, well, we could pick up this line, move it to some other part of the triangle, and that represents 2 new gambles now, and they should choose the same end of that line segment, right? Because all of the indifference curves have the same slope. And if they instead choose the other end, well, then we found a violation of expected utility theory. We found that they have indifference curves that must change their slope over the over the Marshak-Machina triangle. And that's how most of the violations of expected utility theory are found. Okay, and I'll come back to that. When we found that, right, we proposed all these models to try and allow for these differences. It's a question, though, whether when we left expected utility theory because we found these violations in the Marshak-Machina triangle, whether any of these other models that we proposed were right. Dave Bushina long ago made this point. We have a whole bunch of tests that show expected utility theory is violated significantly, but it's pretty meaningless until we actually reject that in favor of a preferred alternative. And we don't have data that really gives us a preferred alternative to expected utility theory, although there have been some attempts, and there might be some people who disagree with me on that. And it's still hard to know whether these violations are actually something that we should care about in practice or not. So let's look at what some of these alternatives are. Right? If we represent expected utility theory as the integral over, essentially the derivative of our distribution function times our utility of outcomes, right? That's our basic model. Almost all of these alternatives are just variations on a theme, right? So Edwards in '62 proposed, well, what if the utility function is that we just value the money for its value, right? So our utility function is a straight line where u of x is equal to x, and we modify instead the probability function using this pi function, which is a probability weighting function. Okay, this led to the proposal for the probability weighting model, which uses a utility function and a probability weight. So it distorts not only how we value x, but it also distorts how we perceive the probability. Quiggin then proposed a variation on this that I'm not going to go into very deeply, but it essentially just allows for that probability weighting model to be transitive, to enforce the transitive property. Chu put in a model that was very similar that also adjusts probability, but it does it in a particular way, and it also has two different functions that modify the way x is valued. Okay, Machina then put in a general expected utility model which changes the utility function conditional on the distribution that's available. And finally, prospect theory, which is probably the most prominent alternative right now, essentially just modifies probability weighting by having a different model for losses and for gains. Okay, but it's basically a probability weighting model. And if we're only looking at gains, we would only look at it. It would be identical to the probability weighting model. Okay, so those are the basic ones. Most often, all of those that have made it into the applied literature can be thought of as being what I would call a modified expected utility model. And a modified expected utility model means either they modify the perception of probability, or they modify the utility, or they modify both. Okay, this doesn't cover all models. There are some others that I acknowledge, but they aren't applied very often. In fact, very, very seldom do they find their way into the literature. And these modified expected utility models have the impact of doing this in our Marshak-Machina triangle. So they allow for the indifference curves to fan out a bit, which represents a sort of changing perception of those probabilities as you get to different parts of the triangle. And this actually mirrors very closely what we observe in the Marshak-Machina triangle with empirical choices. So you might think, well, this is great. We've found some way of representing the choices that people actually make. But there's a problem with this. We've added degrees of freedom to get here, and we're not sure if the degrees of freedom that we added were the right ones. Okay. And here I'm going to start making an argument that's a little bit detailed. And I don't want to go too far into the math behind this. If you are interested, there's one paper in the AJE that I actually did with my father. There's another one that's in the Journal of Econometrics that we co-authored as well, that goes through a lot of this math so you can understand it more thoroughly. But the first proposition is, if we have a general Marshak-Machina triangle and we have, we have an individual that has these preferences that can be represented as a utility function and a probability weighting function, then we could also find, well, we know then that there's a preference function that does not weight probabilities, but that distorts, that has probabilities included in its utility function that represents the identical preferences, as well as another function that has the probability weighting and the utility function separated. In other words, these two models produce exactly the same preferences, but they have very vastly different interpretations and applications in empirically. And this leads to a couple other propositions that are very similar. If we then think about this sort of general expected utility type approach, right? We can then say that for any set of preferences in the Marshak-Machina triangle, we can find at least two distinct representations that pair this utility function and this distribution of risky outcomes that produce exactly the same preferences. Okay, and if that's the case, that leads us to proposition 3, that the only way we could ever possibly estimate our probability weighting function f is by making an arbitrary assumption about what the utility function looks like. Because otherwise, there are an infinite number of these pairs that all produce exactly the same behavior, no matter how many observations we have. So it's arbitrary. It's arbitrary and based on our assumptions, right? So when we go into the literature, this is what the probability weighting functions that we find in the literature look like, right? They overweight these small probabilities, they underweight these large probabilities, right? And this is something that we see regularly and over again. But why are we seeing such regularity in these estimates if it's arbitrary, as we say? Well, it's because of the way they've estimated it. Whenever they've estimated probability weighting, they have made some very restrictive assumptions about what the utility function looked like in order to generate it. The first two who produced this theory of probability weighting assumed that the utility function was just linear, that u of x is equal to x. Kano and Shersky have been able to produce estimates with much sort of more mild probability weighting, if you will, using essentially constant relative risk aversion functions, but they enforce that they are constant relative risk aversion. And all of the estimates that are out there in the literature that produce our estimates of probability weighting only occur when we have a very specific utility function assumed. And thus, we haven't been able to discern utility and probability weighting simultaneously. And why? Because it's not possible. It's not possible. And if it's not possible, well, again, we come back to this question: have we just added a whole bunch of degrees of freedom to mimic this data in the Marshak-Machina triangle without actually explaining behavior? So the evidence for all of these models comes primarily from experiments run in laboratories on college students. Most often, those college students have been American college students or other Western countries. And so it's a little questionable whether this is really, representing important behavior. I can't say. There have been some that have been run outside the labs. There have been some, for example, in Vietnam and in China. And I cite here one that's been done with farmers in France. Most of those have been done with, smaller amounts of money, although some have some serious amounts of money involved. That one in France got up to 6,000. Let me see. I think I'm not sure exactly how much time I have, but I don't want to waste your time on pieces that I can skip. Setting up the, yes?
Yeah, you continue.
Okay, I'll keep going. So setting up the empirics that I'm going to do. Arrow's definition of absolute risk aversion gives us a way of sort of thinking about certainty equivalence, right? He used some very simple math, Taylor series approximations to generate this relationship between a certainty equivalent, the mean of a distribution, and the variance. And it's related through this absolute risk aversion, okay? And that is one way we can actually generate an empirical observation of absolute risk aversion. Now, if people aren't perceiving probabilities the way we define them, or their utility function doesn't behave the way we say, this measure of absolute risk aversion doesn't necessarily relate to a utility function the way we think it would, the way it's defined by Arrow, but it's still some measure of risk and how people behave with regard to risk, right? If instead of the utility, expected utility framework, we went and did the same thing with probability weighting, what happens, right? Well, we can actually use this, use a series of gambles, right? And obtain this certainty equivalent. And the certainty equivalent should be basically linear if we're talking about somebody who behaves according to expected utility theory based on Arrow's work. But if instead we observe this and it's probability weighted, well, it could be that that probability weighting gets loaded into this absolute risk aversion measure. And by loading it into the absolute risk aversion measure, well, it's going to change the shape of that certainty equivalent function. And so that's one way we could possibly see whether we're seeing probability weighting or not, right? So what would it look like? Well, here you can see the derivative of the certainty equivalent with respect to probability is going to end up being some measure of utility, of the derivative of utility, right? And how that changes over the range. That's really what's going to happen here. So observed absolute risk aversion is going to end up being smaller when we see overweighting of probabilities, and and it's going to be larger when we see underweighting. Okay, so you would expect with small probabilities that your absolute risk aversion is going to be exaggerated. It's going to be large, and when you find large probabilities, you're going to find it to be understated, right? And so it should give us this sort of inverse S shape, something like this. Okay. The problem is, so if we have real preferences, this is what the actual function looks like. There's a little bit of a wave to it, but it's basically straight, right? Remember, Arrow is approximating. If instead we put the probability weighting function on it, right, we see that inverse S shape that I promised, with the underweighting and the overweighting. Okay. If we do the same thing, right, but now we do this with a probability weighting with lower probabilities, or excuse me, with larger amounts of money, then we see that this curve flattens out. And by flattening out, it makes it so it's going to be harder and harder to discern what's going on, right? So now with these larger amounts, the S in the expected utility, or I should say in the probability weighting, right, was exaggerated with large amounts, but with smaller amounts, it flattens out and it becomes more of a straight line, which means it's going to be harder to see that it's different from expected utility theory. Though when we get to some of these smaller amounts, we would expect that there might be a difference. Okay, so that's one thing we might look for. There's a little bit of going down a rabbit hole in that if I cut to the chase, we don't end up seeing very much along the lines of this, but it's worth recognizing how these empirical absolute risk aversion actually change. Here again, when we have large amounts, we have regular amounts or sort of standard amounts of money being offered. We get this S curve. If we make the rewards large enough, this S curve just sort of, pushes down to the axis, and we don't see anything. So we can't discern anything there very easily. So this is sort of one way we can't quite get at this. But there are still some things we can do. So what is our data? Our data, we have 584 subjects. They were solicited through a Qualtrics panel. This is a maintained panel of survey respondents in the US. They're stratified by income and gender. And we actually had them complete two sets of choice tasks. The first, they completed a set of experimental lottery choices, which are very common in the literature, right? The amounts and the probabilities were all things that have been used to argue these alternatives to expected utility theory. And then after they had done that, we had them complete a set of choice tasks using New York State lottery tickets. New York State lottery tickets involve very tiny probabilities of getting gigantic amounts of money. Okay, some of them are not extremely gigantic, but most of them do have some pretty substantial amounts of money beyond what you normally see in an economic experiment. The choices then were randomly selected to be incentivized, which is common in this literature. So it should be representative of the types of choices you would find elsewhere in the literature. And the actual payout on average was about $6. Okay, but they were making choices, and some of them almost certainly received large amounts of money through the way this was incentivized. We can't actually measure the winnings from the New York State lottery choices because, well, they had to get the tickets, and the tickets were anonymized, so we can't figure out whether they won or not. But when they chose a New York State lottery ticket, they got that ticket, right? If that was the randomly selected choice. You see our representation, they're about 50% male and 50% female. Age was about 48 and a half. And household income, this is measured in thousands. So they're making about $74,000 on average, which for New York State is pretty close to average. So this is fairly representative of New York State, which we had to do it in the state of New York. We couldn't use New York. It's illegal to send New York State lottery tickets to another state. Okay, so we had to do it this way. Here are what the experimental lotteries look like. So these are dollar amounts, outcome 1, 4, 12, 24, right? So they're not huge. The outcome 2 was either $0 or $4. These are all positive amounts. And the probabilities for outcome 1 are listed here in the first column. So you see sort of the range of probabilities, the range of outcomes that are, and these are, like I said, standard in the literature. You find these everywhere. And this results in this estimated curve that measures the probability of a win against the local absolute risk aversion. And you see this sort of inverse S shape that looks a lot like the probability weighting that we should be looking for, right? Although I told you there are some problems with that. So they're, fairly familiar shape. And maybe that tells us we're looking at probability weighting. Okay, here's the New York State Lottery. And these are all stated in terms of odds instead of probabilities, but you can calculate these probabilities. The probability of winning this, what is it, $40 million outcome is astronomically low, just very, very small, right? And so these probabilities are all smaller than anything you observe in the other, the standard lotteries, aside from this one, where you can get $50 for, with the 1 in 100 odds. That one is actually overlapping with the other, basically. But all of these are going to give you sort of small probabilities of a win, with much larger amounts of money involved, and some, like I say, astronomical amounts. Now, if I plot this, you got to be careful and read this plot correctly. If I plot those experimental plots here, right? So this is what we saw before, only I've limited this now, so we only go up to a probability of 0.25. And I do that so you can see what the plot looks like for the New York State Lottery choices, which is this up here, okay? Which is not located anywhere near this curve, number one. And secondly, has the opposite slope. It doesn't look anything like what the probability weighting should tells us it should look like, right? This is just very different, but at the same time, very different amounts. And so maybe we're just seeing something very different altogether, right? So it's a question whether what we've just seen is enough to tell us, well, probability weighting doesn't make much sense, but it's at least enough to make us question, right? So the real exercise here, and what we're going to do that's going to make this, I guess, convincing in my mind, is we're going to use the experimental lotteries that are common in the literature and try to do out-of-sample prediction to see if they predict the behavior we observe with the New York State Lottery choices. Okay. And the reason behind this, well, this is what we do empirically with estimation, to try and figure out whether we've added degrees of freedom in a meaningful way or whether we're overfitting, right? And that's really what we're going to try and do here. This can help us overcome this identification problem. The problem with it, though, is we have to assume some strict functional forms when we estimate. So there's always that caveat. Perhaps we chose the wrong functional forms, right? What functional forms are we going to choose? We're going to estimate local absolute risk aversion using expected utility with experimental lotteries, and assume CARA, or constant absolute risk aversion, and then predict the certainty equivalent for the New York State Lotteries. We're also going to estimate the common probability weighting function that's out there in the literature using risk neutral preferences and try and predict. And finally, we're going to try and estimate with both CARA and the common probability weighting function and predict. And we're going to use all three of those to see which one of these wins, which one of these is best at predicting the New York State Lottery outcomes. Okay. All of these are sensitive to outliers. All of this is, and so I will tell you, we eliminated those who gave us certainty equivalents that were greater than 2 times the expected value of the gamble, because that's just outrageous. It doesn't actually eliminate all that many people, but there were a few people who just clearly weren't paying attention. Let me put it that way. And I'm not going to go too far into this. This is the first. There's a problem in trying to estimate these functions. And it's a problem that was solved in some work that I did with Travis Libert. And so we're going to end up using a quadratic function to estimate these, because if you use anything else, the parameter is not identified. Okay, so we're going to end up using this quadratic function, and then from there proceed. And here's just a distribution of the certainty equivalence that, or excuse me, the absolute risk aversion that we get when we estimate using that expected utility model. And when we estimate probability weighting, we end up running into the same sort of problem. This is the probability weighting function we're using, which is the most common in the literature. You can find it all over the place. And here's the distribution of probability weighting parameters that we get. And I have explored and tried to figure out, I can't tell you exactly why you get this big concentration right here. There's something numerical going on that I don't think is related to the data. In other words, and I suspect maybe this actually happens with all of these experiments we see, is that there's something numerical driving this estimate that comes out of it. But it looks a little funny. When we estimate jointly, we get something similar in both respects. This represents, well, this axis here is our is the absolute risk aversion, and this axis here is our probability weighting parameter, right? And again, you have this place where you just get a really big bump in the distribution. But the distribution looking across absolute risk aversion looks a little bit more normal. Okay. Okay. So the outcomes. So this is a fractal polynomial fit, and here we're just looking at the extrapolated certainty equivalent. The green line reflects the actual certainty equivalent, right? So our certainty equivalent is represented here on the x-axis. And if we were predicting accurately, this green line would be our estimate, okay? So here we're just using expected utility theory, and you look and, you know, there are significant differences, right? We depart way out here, and we depart right around here. We cross the line here, and it's indistinguishable statistically all along here, right? So there are places where this is getting it pretty close, and places where this is sort of failing. That makes sense. And hopefully this makes sense to you. So now I'm going to show you what it looks like when we add in probability weighting. If we extrapolate using and try and, you know, predict out of sample using probability weighting, this is what our curve looks like. And if you'll notice, the scale of our predictions for probability weighting out of sample, when we take it out to this large of a reward and this small of a probability, are of a scale that green line that's supposed to be 45 degrees is now flat. In other words, this doesn't even come close to fitting. This is off the mark by orders of magnitude. It's not representing at all what people are doing in terms of choice in the lottery gambles when we discern what they did with these much smaller gambles, okay? And well, you might say, well, here we threw away all of the utility information, so maybe it's the fact that we did that. What if we estimated utility and probability weighting together? And again, there's that identification problem, but we did it, and what happens? Well, it's a little bit better, but not a lot. That green line, it's not exactly flat, but it is still nowhere near 45 degrees. And we are significantly different from that green line everywhere, aside from just right out here for these certainty equivalents that are just way out on the end. And when we're talking about these certainty equivalents that are way out on the end, remember, those are the ones on the edge of the distribution. Those are outlier folks, right? So this model may be good at predicting people who are just way out on the very edge of our sample, but it is missing the vast majority of our sample. That is the crux of the outcomes that we see here. These are averages. We're looking at a whole bunch of gambles at once. If we did single gambles, right? So here's a particular gamble with expected value of $3.25 that we're using, we're predicting out of samples for. And you look, and the blue curve, again, it's not exactly like the green line, but it crosses the green line in a couple of spots. And it's really only screwing up very bad out here on the edge of our sample, okay? Where if we look instead at our probability weighting for this particular gamble, again, orders of magnitude off, it doesn't look anything like it. With both, we get something that seems to be okay on either end of the sample, on either edge, but where the vast majority of people are, it's missing the mark. Okay, so this is again to say we get a lot better out of sample prediction with just the EU model than we do with the probability weighting included. Here's one more gamble just as an example with a smaller expected value. And again, so the expected values, the certainty equivalent should be down here. These certainty equivalents are measured in cents, I believe. So this is where we should really be looking to try and predict, and we're not really there, but we're off, well, by a fair amount, by about half, something like that, right? With expected utility. With probability weighting, we're off by thousands of percent and across the whole sample, right? And here with both, again, we're off in, and by thousands of percent in most of the sample. So the conclusion that I draw from this, right, is that if I was going to be trying to use these models, the one that seems to be doing much better at predicting how people are deciding is expected utility theory, ignoring probability weighting, right? We have a few caveats in it, and then I'll conclude. One, the prize increases from a max of 25 to a max of 40 million. That's really gigantic. The minimum probabilities decrease from 0.01 to like almost nil. In other words, we're predicting not just out of sample, but we're predicting like ridiculously far out of sample. And the scale of difference in dollar amounts, which is where the utility function comes in, is probably not as important, if you will, as the scale of difference in the probabilities, where the probability weighting function comes in. And so we're perhaps rigging the game a little bit in the way we did this. And it might be that expected utility theory would perform much worse if we were to do the same thing, only with a much larger scale of dollar values than we have here. And with similar probabilities to the probabilities that they had otherwise. Thing is, probabilities are bounded, so it's really hard to push probabilities beyond what we saw here. We really are sort of hitting the edges of what we can observe. More than that, the lottery is not run by researchers. And so there's a big question as to whether people trust the probabilities that are reported on these lottery tickets. And that's perhaps going to introduce some additional bias that we wouldn't have seen in the lab, right? The conclusion that I draw from this, first, in terms of econometric identification, we're never going to be able to find pure identification of all of these preference functionals. So we've got to be creative in the way we try and ferret this out and figure out what's going on and how people are deciding things. And it's very dependent on our model assumptions. this gives us perhaps one way of moving forward to get at these functions that we hadn't tried before, and that can give us something perhaps that's convincing. And you know, but more needs to be done. I can't say that this is you know, the final nail in the coffin of probability weighting. We need to do this a lot more and do this in a lot of different ways before we can figure out what is valuable in our additional model, you know, components and what's not. And I'll quit right there. Take any questions you have.
So, thank you, David. So if you have any questions, any one of you, okay, Dr. Akash Saxena has a question for you.
Hi, David. It's nice to see you again. It was a very enriching lecture. Because I have never worked in this area, for my own curiosity, I just wanted to know, like, we have different kinds of decisions, production decisions, we have investment decisions, let's say in stock markets, or let's say farmers' participation in future markets, or we have some kind of consumption decisions, or the utility performance or welfare you have shown in your study. So can we apply the similar kind of risk aversion models or risk estimation in different kinds of decisions? And how the probability estimation and the predictive ability change across different decisions, whether it is taken by the farmers as a decision maker or a consumer as a decision maker. Because your study showed that a lot of welfare impacts, lot of variation was there in the welfare impact. For example, the welfare, it varied from $25 to $40 million. And the minimum probability, it ranged from 0.01 to 0.3 10 to the power -6. So a lot of variation, was there in terms of predictive ability of these risk estimations. So just for our own curiosity, I wanted to know whether these models can be applied and what could be the predictive capability of these estimations.
So there's a pretty robust literature applying expected utility theory and prospect theory. So those two separate models, which includes probability weighting, to agricultural production decisions in a wide variety of circumstances. There are also financial decisions. I don't know the agricultural one, so I won't talk too much about that. With the agricultural one, it's very interesting. So they've done several different things. One exercise they've done is administer lab experiment type, you know, choices to farmers to try and gauge their probability weighting function and their utility function, and you know, measure their risk aversion as well as their sort of probability perception, and then see if it is predictive of people's production decisions and other sort of farming decisions that involve risk. And it's not a great fit. So there is some relation. It's a pretty mild relation, if you will. It's extremely noisy. There are other sorts of measures of risk aversion that are index-based, that are not model-based, right? Simply asking people how they respond to risks, whether they feel like they are more risk-averse or risk-loving. There are some psychological measures that seem to have a little more of a correlation with behavior and are a little more predictive. Economists still tend to shy away from expected utility or prospect theory. I guess what I'd say is it is possible to apply these, and we've seen these applied, but there are real problems with them that we're having a hard time grappling with and figuring out, because you're right, the welfare implications are entirely different depending on what those utility functions look like, and that has implications for policy, right?
Thank you.
Linda?
Thank you, David. It's Shivendra here. Thank you so much for accepting our invitation and giving us a very good and useful orientation about alternative proposals of modeling the expected behavior and particularly this probability weighing technique with the case study on New York lottery system. Like my senior colleague, I'm also curious to visualize a case study where can we test the robustness of this alternative proposal, for example, the probability weighing model, particularly in a situation when the expected utility theory is failed to predict the expected behavior. And when I am saying this, I'm visualizing a case study in a situation of COVID, when we expected that in a rationality terms that whenever there is a change in the income or something, then the consumers reorient their decisions and they will reduce the consumption of different commodities and their intensity will differ. And we also found when there was an imposition of lockdown in India, so there was a decline of about 22 to 23% of income. So we started predicting that what will be the expected decrease in the food consumption or something, and established models like utility theory models with the income elasticity of 0.4, 0.5 said this probably there will be a decline in the food consumption with the decline in the income. But when we got some real observed data using some national representative surveys, we found that actually consumers did not behave in that sense. So rationality assumption was violated. So in spite of decline in the food consumption, they showed an increase in the food consumption during that period. So what I was curious to see, can we test your models and see that how robust they can predict those type of expected behavior in a very given situations like COVID or some other sort of things where rationality behaviors cannot be expected. And can we see test both the models, compare the models like probability weight models with the expected utility theories or something?
I think so. I mean, I think there's plenty of opportunities. I mean, so as soon as you have a clear test of rationality and it you know, you can see expected utility doesn't explain this behavior, right? It's possible to go back and now, okay, well, let's try one of these alternatives. Probability weighting would be one of those possibilities. In particular, if you start talking about COVID, you might think about using some of Slovik's models, where he deals very explicitly with the idea of fear, or terror, something that's a little bit beyond just, money risks, if you will. And you could see, if there's some way that that you could use some part of the data where there's a little bit of variation and estimate, and then as things, looking and predicting out of sample to a different part of your data, I think you could do the same sort of exercise and see whether you're getting variation that makes sense, right? The key is to find some way of looking at data where you know you've got a violation of EU. You can explain that violation with added degrees of freedom, right, in your model, and you estimate the model with the added degrees of freedom there, and then take this to some data where the same people are making decisions, and they've the situation has changed somewhat, and is it predictive? Is having those added degrees of freedom more predictive of what's going on than your model before that? That's the key, because you want to know whether you've added things to the model that were actually useful in predicting behavior or not. That's the crux. But I think it's absolutely possible with the type of situation you're talking about.
Shivash?
Hello.
You have a question? You have a question?
Yes, sir.
You have a question?
Yes, sir. Yes, sir. Can you
Okay.
hear me?
Yep.
Yeah.
So
Hello, Professor. Thank you. That was an interesting lecture. I'm not sure whether I got everything right, but I have a question. Is this a case of extreme, for example, would this be a case only in case of like an extreme case, like a windfall gains, or would it be same for other cases in which such extremes doesn't exist?
Yeah, that's totally a possibility. And that could be the case for a couple of different reasons, right? It could be that the caveat that I mentioned at the end, maybe people just don't believe the lottery probabilities, and they treat those in a way that is very, very different from experimental probabilities in a lab that a researcher has told them. That would be one way in which maybe this is unique, and so out of sample prediction just doesn't make sense here. It's not really an out of sample prediction. We've added some other dimension to it that was never measured in the first place, right? But the other possibility is one that I would actually discount. So is it possibility that the fact that we're using these just extreme values of money, people have a different mechanism of deciding over those extreme values of money than they do the smaller values? Is that possible? That's absolutely possible, but if that's the case, it basically already violates the spirit of the models that we're proposing. And it suggests not that we have models that need to be more sparse, or we need to think clearly about what degrees of freedom are actually valuable and which ones aren't. It would be suggesting, well, every time we observe something that doesn't fit, we'll add another degree of freedom, which just compounds the problem, if you will. I don't think that's what's going on. I don't think it's just simply that people have a different decision mechanism as soon as we started talking about the larger amounts. I think it's more just that we weren't really getting at their decision mechanism to begin with.
Thank you, Professor. I thought those games have solved the issue which makes things risk. Now it's more complicated.
Yeah.
Anybody else? Okay, then if there is no questions online and offline, David, I thank you for your very enlightening lecture on risk choices. Anyway, we could not make it possible in a physical mode when you were here, but thanks a lot for giving us your time online to enlighten us on the risk preferences and risk perceptions, risk behavior, and all those kind of things. And I am sure that the probability weighting to the risky choices, what you have discussed here today, it will be relevant in agriculture decision making also, particularly in the context of extreme climatic events that are likely to be in a much more frequent basis in the times to come. Thank you so much. Thank you.
Thank you. Thank you. It was good to be able to present it. Hope it was useful.
Okay, now we can close this meeting.